My talk is about 0-1 loss for the random graph G of P in the case when P equals n to the minus alpha, where alpha is positive number. So let me start from some definitions. So first order properties are the properties that are expressed by first order formula, which are built of relational symbols. The first one is for two vertices that are adjacent, and the second one is for two vertices that coincide. Logical connectivities, variables, and quantifiers. So, for example, the property of a graph to be complete is the first order property because it is expressed by the first order formula, and the property of a graph to contain a triangle is also first order property. But for example, property of a graph to have chromatic number k is not the first order property, it's the second order property. Okay, and I will tell about first order properties of random graph G of P. So we have n vertices, and all pairs of vertices are adjacent independently with probability E. Well, from the famous results of Erdős, Arényi, and Vella-Bolobash, it follows that if we consider any arbitrary graph G and the property of containing this graph, which is denoted by LG, then if P is asymptotically larger than n to the power minus 1 over maximal density of G, then with probability tending to 1, a random graph contains graph G, and if P is asymptotically smaller than 0, then the limit probability equals 0. And if P equals this threshold probability, then the limit exists, but it doesn't equal either to 1 or to 0. And we can note that if we consider a set of all following properties, we take all properties of containing a graph G, all negations of these properties, and then if P is n to the minus alpha, where alpha is positive irrational number, then either the probability of such property tends to 1 or tends to 0. Because all threshold probabilities from this theorem equals to n to the minus alpha, where alpha is rational. So if we have irrational alpha, then probability always 0 or 1. And the results of such type are called 0-1 loss. So if we take some set of properties, and for any property from this set, either its probability tends to 1 or tends to 0, then we say that the random graph obeys 0-1 law. And we always consider the set of all first order properties, and in this case, we just say that the random graph obeys 0-1 law. And from previous slide, it follows that we have such weak variant of 0-1 law for all, not for all first order properties. But in 1988, it was proved by Spencer and Shela that if you consider a set of all first order properties, and any P equals m to the power minus alpha, where alpha is rational, then we have 0-1 law. And when alpha is rational and alpha is from interval 0, 1, then 0, 1 law doesn't hold. And the question is, can we find some big subset of the set of all first order properties such that 0, 1 law holds even for some rational alpha? And the answer is the following. We can consider the class of properties expressed by formula with quantifier, with bounded quantifier depth. So let me remind the definition of quantifier depth. If we consider formula x equals y, or x is adjacent to y, the quantifier depth of this formula equals 0. If we have a formula phi with quantifier depth equals a, and we consider negation of phi, then the quantifier depth is still k. And if we consider two formula and make some logical operations, we have quantifier depth equals maximum of k and k2. And if we add a quantifier to some variable, then quantifier depth equals k plus 1. Well, for example, if all quantifiers are in front of the formula, then quantifier depth equals the number of quantifiers. And we can consider 0, 1 k law. So it is 0, 1 law for the properties with that expressed by formula is bounded by k quantifier depth. And if for any such property probability tends to 0 to 1, we say that the random graph obeys 0, 1 k law. And we denote by pk the class of all such p that g of np follows the g of np obeys 0, 1 k law. So of course, one property can be expressed by different formula. For example, in this case, we have one property and two different formulas. The first formula have quantifier depth 2, and the second one have quantifier depth 3. So in this case, we take the minimal quantifier depth. So let us consider once again probability n to the power minus alpha. And so we know from the theorem of Spencer and Shiller that if alpha is rational, then 0, 1 law doesn't hold. But it is very easy to prove that if alpha is from 0 to 1 over k minus 1, then even if alpha is rational, then 0, 1 k law holds. So we have k law. The method of proving is very simple. It's similar to the method from theorem of Zhukovskii, Kogan, Login, and Talanov that was proved in 1969. They prove that if p, well, they just consider constant functions, but their proof, using their proof, we also can prove that the result holds for such class of p, that minimum of p and 1 minus p multiplied by n to the power beta tends to infinity for any positive beta. And in this case, 0, 1 law holds. So if we use their proof, we can have this result. But what happens when alpha is greater or equal to 1 over k minus 1? So, of course, we can consider a property of contain some graph G and take threshold function. And when we take this threshold, we have a function p such that 0, 1 node doesn't hold. Because in the threshold we have a limit probability which is not equal to 0 or to 1. But if we consider the most dense graph with k vertices, it's kk, then we have alpha equals 2 over k minus 1. But we still have this interval from 1 over k minus 1 to 2 over k minus 1. And in this interval we also have points when 0, 1 k law doesn't hold. In 2010 we proved that if alpha is in this interval from 1 over k minus 1 to 1 over k minus 2, 0, 1 k law holds. Oh, I'm sorry. And if then we have here, and if alpha equals 1 over k minus 2, then we have such properties that the limit probability doesn't equal to 0 or to 1. Well, we can also consider the interval which is close to 1. So here we consider dense subgraphs, and we also can consider sparse situation. And this is the situation when alpha is from 1 over 1 minus 1 over 2 to the k minus 1 to 1. So alpha equals 1 minus 1 over 2 to the k minus 1 plus beta, where beta is some positive number. And in this situation, when b is a fraction, is a rational number a over b, where a is greater than 2 to the k minus 1, then 0, 1 k log holds. But we don't know what happens when alpha is, when a isn't greater than 2 to the k minus 1. But we have some information about such points. So on this slide, first of all, I will say that a point is critical when 0, 1 k law doesn't hold. So this point is critical. And we have some critical points for this interval, and maybe you can see it here. Well, important is that if we consider the case b equals 1, then if we consider the case b equals 1, then we have beta from the set from 1 to 2 to the power k minus 1. So all points except the last two from this set are critical, and all other are not. So if beta is from this set, then we don't have k-log, and if beta from this set, 2 to the k minus 1 minus 1, and 2 to the k minus 1, then we have k-log. And we also have some results for b greater than 1, but it's not so important. The method of proving is similar. So once again, let me consider all critical points if when alpha goes from 0 to 1. So the first one is 1 over k minus 2. Then we have a large gap from 1 over k minus 2 to this point, and we know nothing about it. Then we have critical point, the first critical point, 1 minus 1 over 2 to the k minus 1. Then we have some points, and we don't know are they critical or not. And then we have the last 2 to the power k minus 2 minus 1 points that are critical. And the last one is 1 over 2 to the k minus 2. No, the last one is 0. Let me now consider small k. So we can see that if k equals 3, then we don't have any critical points in 0, 1 interval. And if k equals 4, then for any alpha from 0 to 1 over 2, we have 0, 1 law. And if alpha is from 13 or 14 to 1, we also have 0, 1 law. And we have one new result for alpha from the last one, from 12 over 19 to 2 over 3. So maybe it's difficult to see it on the slide, so I write some important things on the board. So when alpha is from this interval, then 0, 1, 4 law holds. And when we take the endpoints of the intervals, then 0, 1 law doesn't hold. So on this slide, I just put all these points on 0, 1 interval. The second line is for any k, and the first one is for k equals 4. And I have some time to say a few words about the proof of 0, 1 laws. So all proofs are based on the Ehrenhoff game. It's a game which was proposed by Ehrenhoff in 1960, and we have a theorem that we use to prove 0, 1 laws. It was also proved in 1960. So the rules are the following. We have two graphs and two players, spoiler and duplicator, and we have also k rounds. And in each round, the first player, spoiler, chooses any graph and chooses any vertex from the chosen graph. And then duplicator in that round chooses another graph and any vertex in that remaining graph. And duplicator wins if after k rounds the induced subgraphs are isomorphic. So for example, spoiler chooses red and duplicator chooses blue, you can see. And after 4 rounds, we have 4 vertices and the induced subgraphs are isomorphic, and so spoiler wins. I'm sorry, duplicator wins, of course. Spoiler wins if they're not isomorphic. And the theorem is the following. So I just give formulation of the theorem for the case of graphs, and we have the similar result for any structures, finite structures. So if you have 2 graphs, then for any property expressed by formula with quantified depth bounded by number k, the following 2 statements are equivalent. First of all, the graph G follows property L if and only if with the graph H follows the property L, and the second one is duplicating as a winning strategy in the game on these graphs on K rounds. So, for example, consider these two graphs, and the first one doesn't have a triangle, and the second one has a triangle. So, a spoiler can, if you have a game on 3 rounds, a spoiler can choose these 3 vertices, and he chooses a triangle, but the duplicator cannot choose a triangle in the remaining graph, and so spoiler wins. And the important corollary which we use when we prove 0-1 laws is the following. So the first one is for 0-1 law, and the second one is for 0-1 K law. Of course, the second one follows from the first one follows from the second one. Well, 0-1 law holds if and only if for any natural K almost surely duplicated as a winning strategy in LF4 game on K rounds. And the second one is random graph from POB 0-1 K law if and only if almost surely duplicated as a winning strategy in the game on K rounds. So if we want to prove 0-1 law, then we should just find winning strategy of duplicating. And finally, some open questions. So there are a lot of questions. I just include the questions that I like more. The first one is what happens when we, in the interval from 1 over k minus 2 to 1 minus 1 over 2 to k minus 1. So we have one interval inside this gap, in the case k equals 4, but for all other k we don't have any result. So the second one is the following. In 1988 it was proved that there exists a first order property and an infinite set of rational numbers in 0-1 interval such that for any such rational number, probability of this property doesn't tend to 0 or to 1. So from this result, it follows that for any, there are such k that we have infinite number of critical points for such k. And the question is, are the number of critical points is infinite in the interval, in this interval from y minus 1 over 2 to the k minus 1 to 1. So from our result, it follows that if we add here any positive constant epsilon, then the number of critical points is finite. But we don't know is this number finite or not if we consider this interval. And the last question is what happens for small k. So we have some results for k equals 4. And but we have a lot of gaps, and we are also consider k equals 5 and so on. Thank you very much.
Any questions, comments?
Yes. So for k equals 3, duplicator always wins. Is what you said.
Yes.
Okay.
If alpha from 0 to 1,
For
then
any alpha.
yes.
And for k equals 4, already the number of critical points is infinite.
Yes, it's a question. We don't know.
Any more questions? Okay, let us turn this figure once again.